I think we're live, Ashley.
All right. Welcome, everyone. Thank you for joining us for today's webinar. My name is Ashley Stoneburner, and I am in charge of social media outreach at Bibliotech. Born during the COVID-19 pandemic, Bibliotech is a suite of tools designed to improve the flow of communication and ideas in the construction industry. A little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your control panel. As we have a lot of material to cover, we want to answer most of the questions near the end. The title of today's presentation is The Air Vapor Barrier Must Die and is presented by Joost Fanu. Joost has over 10 years of experience as a specifications writer. He is also a building science specialist registered with the Building Science Specialist Board of Canada. Joost wears many hats. He heads an independent specifications writing firm called JMF Technical Documentation Solutions based in Toronto. He is also a sessional lecturer at Sheridan College in Mississauga, Ontario, where he teaches the specifications course. And last but not least, he is the founder of Bibliotech and Bibliotech Academy. Without further ado, Joost, please take it away.
Thank you very much, Ashley. Can everybody hear me? You can type in the chat. No? Just making sure. Yes? Okay, perfect. Good. Thank you very much for joining us today for this presentation. Thanks for this introduction, Ashley. So today we're going to talk about air barriers, vapor retarders, and a whole lot of different and confusing terminology. So I guess that if you've joined us today, at one point you must have asked yourself, do I need an air barrier, or do I need a vapor barrier, or do I need an air vapor barrier? What's the difference? I don't know. Perm ratings and all kinds of confusing terminology. So I hope to clarify some of these things today. Obviously, there is a lot of information out there in the industry, and we can't possibly go over it all in 1 hour. But what I'm hoping to do is to kind of like go back to some of the basics and try to understand how we got the terminology that we're using today, and also try to analyze if there's better terminology that we could be using. Today's objectives are understand the fundamental difference between air leakage and vapor permeability or vapor diffusion in building assemblies, learn about the history of the phrase air vapor barrier and why its use might be misleading or confusing. And we will talk about kind of like the consequences of using imprecise language in construction documents. So why are we here? Frankly, because we don't like water. At least not in our buildings. Please drink your 8 cups of water a day. But we don't like it in our buildings. When it makes its way into our buildings, that's usually a bad thing. Our clients get pissed off. We get uncomfortable. I have had personally to experience water leakage at my own place of residence. And it's not a fun experience. And also, I hope, we also don't like bad terminology. So those two things have kind of like at least pushed me to rethink about this term air vapor barrier, because at one point I too was very confused, and I was always asking myself, well, which is the right one to use here? Is it an air barrier? Is it a vapor barrier? Is it an air vapor barrier? What's the difference? Are they all the same thing? Never quite sure. Now, one caveat, though, I know that there are people joining us from all over. We will be talking mostly about these assemblies and these materials in the context of colder climates. So since we're based in Canada, that's where the emphasis of this presentation will be. Nonetheless, the physics are universal, and they remain the same wherever you are located in the world. So the stuff we're going to talk about today is going to be useful to you no matter where you're located. So water damage hurts us and hurts our buildings. No matter where you are, if you've experienced water damage in your building, it's a very comfortable experience, and it can lead to a number of nefarious things such as the decay of wood and corrosion of metals. And you can also imagine that that could use to structural failures in certain building materials, negative effects on indoor air quality, proliferation of mold, mildew, other biological contaminants, reduced capacity and strength of building materials, reduced thermal resistance due to insulation wetness. That's a big one because once your insulation gets wet, it's no longer effective. Damage to occupants' contents. I've been on the receiving end of that, and negative aesthetics on the buildings. We are all architects or designers to some extent, and we take pride in the work that we do. So having a building that is ruined by moisture damage, it's not a good thing for us or for our reputation. And water damage also costs us money. In Ontario, in Canada, architects paid about $10 million over the 5 years from 2006 to 2011, litigating issues related to water damage. So that has had quite a significant, it was serious enough that the Prodemnity, the insurance, the architect's insurance company wrote a book called the Prodemnity Claims Experience book, and developed a checklist, which we'll share at the end of this webinar, to just kind of like make sure that like architects understand or are more careful with their design and their detailing when it comes to water management. And if you're in Canada or in other locations in the US, you've probably heard of this term called the leaky home or the leaky condo crisis, where poor education on water and poor water management has led to quite serious litigation and quite serious impacts on the health of the various occupants of those buildings and homeowners. The problem with water is that it's shape-shifting, I like to call it, because it's a really strange substance, and we drink it every day, we deal with it every day, but we never, often we don't take the time to think about all the things water can do and all the ways that water is weird, if you will. So water is one of the only substances that exist naturally in all three states of matter. So you have water as ice, that's a solid, water as vapor or steam, that's a gas, and you also have liquid water that you drink. Another strange thing is that water expands when it goes from liquid to solid. If we remember our physics or our chemistry classes, as things heat up, they typically expand, and as they cool down, they typically shrink. But water does the opposite. So that creates some problems for us in buildings, such as frost heave, for example, of foundations, when water turns into expands and can potentially lift off the foundation of a building. But to understand these different phases and these different aspects of water, there's something called the phase diagram of water, and you probably remember this from chemistry class. But it's essentially a diagram that correlates the atmospheric pressure, and at sea level, it's about one atmosphere. And as you go up, so if you went up to the mountains, you would have reduced atmospheric pressure. And it relates the atmospheric pressure with the temperature. So at 0 degrees Celsius and at 1 atmosphere, you have a freezing point, right? So this is where the water would turn to ice, or vice versa, where the ice would turn to water. So that's one of the interesting points on this graph here. As you increase that temperature, obviously we all know that when you boil it to 100 degrees centigrade, and again, I'm in Canada, so I will speak mostly metric. So you increase that to 100 degrees Celsius, you have another phase change where the water turns into steam. But what interests us, or what is strange to us for as building scientists and building experts, is that between 0 and 100 degrees, depending on the atmospheric pressure, the water can exist both as a liquid and as a vapor, right? So the air that we're breathing right now, it's full of water vapor. So there's quite a bit of water vapor in the atmosphere in general. So that's where it makes it very difficult for us to manage, because we can definitely fight what we can see, but it's harder to fight something that's invisible. So what is vapor? Simply put, water vapor is water in its gaseous or gaseous state. Water can turn from a liquid or gas as a result of two different processes. You have vaporization and you have evaporation. Vaporization, we all know it from boiling our tea, making our tea in the morning. That's the process of heating water up to a boiling point, and bubbles are produced, and then it turns into steam. So we call that vaporization. That's not usually a concern to us, at least not yet. We will see with climate change. But generally, that's easy because we don't heat those temperatures in our buildings. And then we have evaporation. And that's a process by which water turns to a vapor below the boiling point. And that can be a concern for us as architects and as designers, because the more vapor there is in the air, the more potential there is for that vapor to turn back into a liquid. And that can, if that happens in the wrong location in our assemblies, then we can get ourselves in trouble. So there's something called the vapor pressure, and every liquid has this. So it's basically a measure of the material's tendency to transition from gas, from liquid to gas. And it basically, if you think about it, it is, if you take, well, why does, leaving a glass outside, we're not boiling it, but all of a sudden, if you leave that glass outside for a while, you notice that that glass gets empty. So where does the water go? And how does that process happen? So if you think about it, well, what happens is, even though the water is a liquid, and we know that, from our science classes that, particles in a solid are fairly tightly arranged. In a liquid, they're more loosely arranged, and in a gas, they're very loosely arranged. But what it is really is, at the surface, at the interface of the liquid and the gas, what you have is that there are some particles that have more energy than others. And we talk about this concept of energy, which is really an amount of how much kinetic energy or how much moving energy there is in the material. So these materials have more energy than the others, so they're able to actually escape into the atmosphere, because they get heated. They get heated by heat rays, like they get warmed up because they are at the surface here, or they get carried away by the wind, right? So there is that tendency that at the surface, at the interface between the liquid and the gas, there's a transition happening. And this tendency for this to happen is called the vapor pressure. And that's really important to us in our buildings, because we have to figure out what that tendency is at different locations in our assemblies. And that has a tendency to change with temperature, obviously. So we talked about vaporization and evaporation, and the reverse is condensation. And what really happens with condensation is the same particles that had quite a bit of energy, now when they are in a cooler space, so if the temperature gets decreased, remember we said that the energy that the particles had allowed them to escape. So if you remove that energy, they will slow down. So those particles will slow down, and they will eventually, the molecular forces between them will take over, and then they will turn back into a liquid. So, what really is guiding all this is temperature. And temperature really, from a physical or physicist standpoint, is the average kinetic energy of all the particles in a substance. So it's, if we measured how fast all these particles are moving, that would represent their temperature. So as we add heat to them, they get quick, faster and faster. As we remove heat, they get slower. So that's what permits them to either escape into the vapor phase, or, as we cool them, they condense back into a liquid. So temperature is really, really important in kind of like understanding these air bearers, vapor bearers, and other materials. So now, if we look at all these processes happening, there's another very important process that happens over time, and this is kind of like a fundamental law of nature, if you will, and it's basically the second law of thermodynamics, which states that the amount of entropy or disorder in the universe is going to keep increasing unless we put energy to reverse it. And what that really means, I like to kind of like characterize it as saying that, well, nature is fair and has a tendency to equalize. So what happens with diffusion is you have these kind of like water molecules that want to equalize with the balance of the molecules around them, to kind of like create a fair distribution, if you will. And what that does, like, there are two main things that affect it, and they are the difference in temperature. So we talked about that. And then the difference is in concentration. So if I have more particles in this location and less particles in this location, these particles will want to move over here to kind of like balance things out, if you will. Okay, again, I'm trying to cover as many bases as possible. So I want to answer the fundamental questions, if you will, the questions that we don't often ask, right? Like we're like, okay, what is air, right? Air is air. Why are you asking me this question? But if we think about it, air is simply the mixture of gases that make up our atmosphere. The Earth is kind of like surrounded by this mixture of gases, and in proportion, we have about 21% oxygen, 78% nitrogen, and about 0.9% argon. And inside this mixture, there is some space for water vapor. So depending on the temperature of the air, you can have anywhere between 0 to 4% water vapor. So remember, we talked about these kind of like molecules escaping into the air. So it's not a constant, and it really depends on the temperature. So the ratio of the moisture carrying capacity of the air to the amount of moisture it currently holds is called the relative humidity. And I'm going to explain that a little better in the next slide, I hope. But one thing to remember is that relative humidity is relative. It's just that. So when we say, for example, that we have 50% relative humidity, if we imagine the air as being like a glass or a cup or what have you, imagine that cup being half full. Now, this is just for picturing purposes or for illustration purposes. What happens at the physical level is slightly different. But for our purposes and for the purposes of approximation, this is good enough. So at 10 degrees Celsius, that water, the amount of water in that air at 50% relative humidity, so if it was half full, would be about 5 grams, right? So the air could carry potentially up to 10 grams of water. So that would be 50% relative humidity. If for some reason that air was heated up to 20 degrees Celsius, what we would notice is that this same 5 grams, and we didn't change the amount of moisture at all, would now become 25% relative humidity, because the amount of water that can be put in this now container of air, if you will, has doubled. So that 50% at 20 degrees has now become 25%. And then if in the opposite, we were to cool the air down to 0 degrees Celsius, the same amount of moisture would now become 100% relative humidity, because at this temperature, the air wouldn't be able to hold any more water, and then that's what we call the dew point, because any extra moisture that get put in this air would condense and would just turn into liquid. So keep in mind that concept, and that's very important because relative humidity is relative. So if anybody gives you a relative humidity value without giving you the temperature or other characteristics of that air, it's really a meaningless value, because without knowing what temperature you're dealing with, 50% relative humidity, 100% relative humidity doesn't mean much, I guess, in terms of knowing how much moisture you have in the air at that point. So since we have kind of like established some of these baseline criteria, now we can look at, well, how does water vapor move into our buildings? And there are two main processes for that to happen. So we have diffusion and we have air leakage. And our industry tends to focus, well, not as much anymore, but has historically focused on diffusion. But we will see that air leakage is just as important, if not more important. So what's diffusion? Basically, it's the movement, as we've said before, it's the movement of water vapor particles from an area of low concentration to an area of, from an area of high concentration to an area of low concentration across some kind of temperature gradient. And then that we've also seen that that's caused by movement of particles at the molecular level. And that's not really caused by air pressure. So what that means is, really, if you want to think of diffusion, you can imagine a balloon that's pumped up with air. You leave it out a couple of days. Even if this seal was completely airtight and you had a perfect seal, what you notice after time is that that balloon would lose some of that air. And it's because of that tendency of the particles to want to equalize, basically caused some of that, those, I guess, air particles on the inside of the balloon to quote unquote leak out. But they're not necessarily leaking out through an imperfect seal. They're leaking out literally across the membrane, because no material, no matter how perfect it is, there's still some microscopic pores through which particles can leak. And then that affects our buildings in several ways. So if you imagine cold climate like Toronto, in the winter, we have usually a cold exterior. And remember, again, colder air, lower moisture carrying capacity. So this air would likely be very dry. And then here we have a warm interior, warmer air, more moisture carrying capacity, and we have all kinds of activities that produce moisture inside the building, such as breathing, showering, cooking, and all kinds of activities that would produce moisture, that would let moisture in the air. So what would happen is you would have these particles wanting to equalize with the outdoor, and they would travel across these materials to the outside. And this is very important to us, because if we don't pay attention to the temperature profiles of all these materials, you could have a very cool surface where the molecules would just condense back into into liquid water, and that's where the damage happens. So that's pretty much why we need vapor barriers in our buildings, or that's why vapor barriers were introduced in our buildings, to stop that from happening. And you can imagine, and the thing is, condensation in our building assemblies will always happen. The most important thing is to control where it happens, so that it happens in such a way that it doesn't damage moisture sensitive materials. So if you had, sheeting that was kind of completely non-reactive to moisture, then you could let the condensation happen there, or that's where you would want the condensation to happen. So in the summer, we actually have the reverse process happening, because we have air conditioned buildings, and we usually have hot and humid outdoors. that will then push some of this moisture back into the building. And then our vapor barrier, usually polyethylene or what have you, would become the condensation surface. So the condensation is happening, but we just tolerate it, and then we realize that we can kind of like just live with it, because over the course of various seasons, we are expecting that moisture to dry out. So we've come to our first term, vapor barrier. What is it? So according to the National Building Code of Canada, the vapor barrier is described as the elements installed to control the diffusion of water vapor. And that term, diffusion, is very important. So how is it measured? So we measure vapor barrier effectiveness in perms, and that's a unit of mass, time, area, and pressure. So it's essentially 1 grain of water vapor per hour per square foot per inch of mercury. So that's mass, time, area, and pressure. So we're trying to measure all these things across the profile. And 1 grain of water vapor is really, really minuscule. That's 65 milligrams. That's really tiny. Like a grain is approximately the weight of a single grain of wheat or barley or something like that. So it's a very small unit of measure. In metric, that would be about 57.2 nanograms per second per square meter per Pascal. But we're in Canada, we speak both. And pay attention to vapor barrier type. So when a manufacturer or somebody tries to sell you a material, they might say, oh, this is a type 1 vapor barrier, this is a class 1 vapor barrier, what have you. It's important, I always say, to know what standard they're measuring to. So in Canada, we use the CGSP 5133 standard. That's what's referenced in our building code. And there are essentially 2 types of vapor barriers. One is low permeance vapor barrier, so about 0.26 perms. And then the type 2 vapor barrier is about 1 perm. So, and that would be called the standard permeance vapor barrier. In the US, they have 3 classes. And I like their classification, the classification system in the US a little bit better than in Canada. But our understanding was borrowed from what we did, and they made it better. So in the US, they have 3 classes of vapor retarders. They don't call them vapor barriers. And class 1 vapor retarder would be less than or equal to 0.1 perm. A class 2 would be between 0.1 and 1 perm. And a class 3 would be between 1 perm and 10 perms. And anything above 10 perms would be considered vapor permeable, so it wouldn't be a vapor retarder anymore. And there are a bunch of different types of materials that that fall into all these kinds of categories. So a class 1 vapor retarder is typically like a polyethylene sheet, so that's usually an impermeable material. Class 2 would be something like foil, or like as used in foil-faced insulation or craft paper. And class 3 would be paint, right? So paint is a type of vapor retarder because it does slow down some of the moisture entering our buildings. So vapor barrier, vapor retarder, what's the right term to use? So in the US, there was a lawsuit. And basically in the 1970s, it was decided that we wouldn't call things vapor barriers anymore. We call things vapor retarders because there was a court case where the owner sued the contractor because they didn't provide a vapor barrier because there was evidence of water in the cavity behind the vapor barrier. And the judge decided that if it was a vapor barrier, it would exclude all water. So it's not a barrier if it doesn't stop all flow of water. So as such, they changed their terminology to retarder instead, which it makes sense. But then why do we still say air barrier? Because in a sense, air barriers still let air into the building. So using that logic, the industry should also change to an air retarder, but that sounds even weird just saying it. So what would affect vapor retarder selection? One important factor is climate. in the US, there are many more climate zones than there are in Canada. And according to the International Building Code, or ASHRAE 90.1, if you will, the climate zones are qualified or put in different categories, going from warmer to colder as you go up north. And I think from drier to wetter as you go east-west. I don't remember. But in Canada, most of our climate is considered cold. So that does help us a little bit in our wall assemblies and our wall assembly selections, because we don't have to deal with as many different climates, if you will. But that might change because of climate change, right? So as things get progressively warmer, as we have more and more freak weather, as weather patterns change, that will affect our wall designs. Basically, the rationale in the National Building Code of Canada is that since there are very few climates, even the milder ones like British Columbia climates, that would not need some kind of control of vapor diffusion, there's a recommendation, and in Part 9 of our building code, it's pretty prescriptive to install a vapor barrier on the quote-unquote warm in winter side of the insulation. So that's the recommendation in Canada. In the US, you would need to consult the different US building codes, but US codes are written in a very prescriptive way. So they tell you exactly what you need to do for the different climates zones that you're in. But generally, the conventional wisdom is the warmer your climate is, the less requirement there is for a vapor barrier. And if you add one, you could potentially run into issues. And the other factor that would affect vapor retarder or vapor barrier selection would be the type of facility that you're designing for. So if you had a specialty type facility, such as a swimming pool, a walk-in freezer, or an arena, you would need to kind of like look at that a little bit more closely to determine, how are the environmental conditions that you're creating inside this facility different from the outdoor conditions, and properly locating any kind of like moisture control membrane or vapor barrier membrane in that assembly. I would suggest running some kind of hydrothermal simulation to do that. And here I'd like to point out that a lot of the rules of thumb, if you will, or approximations that we have in our building codes also stem for, I would say, lack of computing power or lack of technology at the time. And we're going to look at some of that history a little bit later. But now that we have, software such as Woofy and other hygrothermic simulating software that can help us analyze walls over a given time period and over changing weather patterns, that would help us make more informed decisions. And there are tons of manufacturers that will even offer those modeling services for free to architects and designers to help them determine how best to or what the risk level of certain walls that they're proposing are. So if you're not sure, reach out to a manufacturer and have them help you determine what the best way, or a building modeling expert help them determine what the best solution for your particular assembly is. So what about air? So we talked a lot about vapor. What about air? So air is a fluid, and we talked about it. We said that it's basically the mixture of gases that make up our atmosphere. But unlike diffusion, air moves due to differences in atmospheric pressure. And so basically, if you imagine kind of like the Earth, as the sun heats up the Earth, it creates kind of like uneven heating and cooling areas on the Earth. So that forces air to move from areas of high pressure to areas of low pressure. basically creating, currents or winds or what have you. And in our buildings, we also create pressure differentials due to three main factors: stack pressure, fan pressurization, or wind pressure. So with stack pressure, basically, you've probably heard the term before, hot air rises, cool air sinks. So the taller we make a building, the more there's that tendency for air to enter the building at the bottom and kind of like rise at the top. And as that happens, it creates a pressure profile across the building, and that can result in potential air leakage. And we're going to see why air leakage can be an issue. So you can kind of like imagine this air pulling on the facade and pulling on the roof as it's trying to escape the building. Then there's mechanical pressurization or fan pressurization. So as we ventilate our buildings, if we don't design our mechanical systems properly, we can kind of like create unexpected pressure profiles across the building. And that can bring in air from undesired or undesirable sources. So it's really important to have your mechanical engineer on board with your design, and for them to understand what kind of like airtightness metric you're trying to target, so that they can design the mechanical system accordingly. Also, with the rise of the rise of COVID and pandemics, indoor air quality has really come to the forefront. And then the last but not least is wind pressure. So we can imagine that as our buildings are kind of like hit by the wind, we have a wind facing side, and then we have downwind facing side called the leeward side. So this is the windward side, and this is the leeward side. So this is under positive pressure, this is under negative pressure. So we said air moves from areas of positive pressure to negative pressure. So that basically creates a pushing effect on the windward side and a sucking effect on the leeward side. And that can also result in kind of like different air pressure profiles in our buildings. So air is not just, this mixture of gases. Air is also a carrier of pollutants, or a transport mechanism, if you will. And it moves things much faster than vapor pressure, if you will. So when designing for air tightness, and I haven't touched on what would be kind of like the benefits of air tightness, but when designing for air tightness, it's really important to pay attention to penetrations and transitions and interfaces of materials, because that's where most of the air leakage happens. And air doesn't just carry things by molecular forces, it carries things by what's called bulk flow. So what can air bring into your building? Well, dust, pollen, ozone, smoke, sound, all these things, but also water vapor, right? Remember, we said that there's a bunch of water vapor in the air, and it can also move heat, right? It's called convection. So those two factors are of especially importance to architects and designers, because we want to know how much water vapor we're bringing into our building. And if we bring in too much, we have a potential for that water vapor to condense and to turn back into water and to create all the things that we said weren't good for us. But heat also for energy saving purposes, right? So building airtight has several advantages, like energy efficiency. So I think it was calculated, I believe it was a study by RDH or Morrison Hershfield that showed that you could save close to 30% of energy just by kind of like controlling air in and out of your building. And the important thing to stress out here is, it's not that we don't want air into our building. Of course, we want to ventilate our buildings. We want fresh air into our buildings, but it's just that we don't want uncontrolled air leakage to come into our buildings, because if we don't know where it's coming from, it's harder for us to control how that air moves. Building airtight increases durability of the building because obviously we don't have that risk of condensation anymore. So if once our materials stay dry, then our buildings are more likely to last longer. And obviously with COVID and with the rise of new pandemics, we have this new focus on indoor air quality. So building airtight would really control, where we want the air sources from and how polluted or unpolluted that air is. So it has several benefits. So the way to control that would be to use an air barrier system, and that's an assembly installed to provide the continuous barrier to the movement of air. So that's measured in liters per second per meter squared, or you could use a volumetric flow rate, if you will, in air changes per hour. And generally, it's a unit of volume and time across a pressure differential. So, because in order to move the air, we have to create a pressure differential so that that air can move. So basically, how much air goes through a given material due to air movement at a given pressure differential. So there has been a historical focus in Canada and I guess until recently in North America to measure the air tightness of the materials alone. So the building code specifies how airtight the air barrier material is. So that would be like the sheet membrane or what have you that you would install in the building. And then the rationale was that if you used enough of these airtight materials, eventually the building would be airtight. But what they found is that the air leakage doesn't happen in the plane of the wall because that's usually perfectly fine. It happens at penetrations or at joints or transitions between different materials. So there is now a rise for assembly airtightness testing or whole building airtightness testing, where you're trying to figure out how well the entire building is, how airtight the entire building or assembly is. And there are several standards that test this, and some of them are very specific to the different types of systems. So I can possibly go into all of them, but what I will do is after this session, I will share a summary of standards that I've come across. But for air barrier materials alone, in Canada, we use the ULC S741, which caps the air leakage at 0.02 liters per second per meter squared at the pressure differential of 75 pascals. And then we also have another standard, which is S742, which speaks to assemblies. So that has various classifications, so you can kind of like see how well an assembly performs. And I think that was really smart of them to do it like this. And in the US, this is a standard method, but there's no minimum. So just specifying that, the air barrier system must meet E2178, ASTM E2178 doesn't really mean anything because it's just a way of measuring the air leakage. Is not really a way of like setting a boundary. So you have to specify what is the maximum air leakage that you want per that test method. And then it's important that the air barrier acts as a system, not just a membrane. So it's great if you have a membrane in the plane of the wall, but you need to put that membrane together with so the membrane would be called the material, and then you need to associate that with the different accessories such as tapes, sealants, or what have you, and join that to the components, which are kind of like pre-manufactured elements such as windows, doors, and whatnot, to make the air barrier system. So it's important to think of it as a system approach as opposed to just a material approach. And these are the various leakage rates that are specified by S742. So you have A1 to A5, and then the leakage rate ranges from 0.05 to 0.5. Sorry, my alignment is a little bit off here. And to be effective, obviously, like how good is your air barrier? Well, your air barrier must be impermeable, right? So it needs to be able to not leak air, right? Like that's a basic, a given characteristic. It needs to be continuous, and that's where you have to really pay attention to joints and transitions and openings and things like that, because that's really where a lot of the leakage happens. And there are actually studies that have shown that, very tight, I guess, assemblies are really good because they don't bring in so much moisture. And very leaky assemblies are also okay because they leak so much that eventually the heat dries off the moisture accumulation. But it's when you have in between assemblies where you have just enough leakage to have moisture accumulation, but without enough drying or air passing through it, that you really get yourself into trouble. So obviously we don't want to build leaky because that has energy implications. So we are trying to get as tight as reasonable. And obviously the air barrier system must be durable because it will be exposed to all kinds of pressures such as wind, construction, kicking the materials, and all the stresses that will be exerted on the material once it's in use in the field. What can you use as air barrier membranes? This picture is not an endorsement of any specific manufacturer or product, but there are a bunch of them out there, such as self-adhering sheet membranes, polyethylene, if the joints are sealed and the penetrations are properly sealed, can be an okay air barrier. It's not the best thing, but in most of the houses that we build, the residential construction that we have, polyethylene does quite of the air barrier job function, right? Because the house wrap is not really that airtight a lot of the times, at least the way it's installed. Spray foam insulation, depending on the characteristics and the thickness, and then some sheathing materials now have been introduced where if you tape all the joints and then you seal all the penetrations, it could work as a decent air barrier system. And then this is one thing that's really important is we have to remember that diffusion is a really, really slow process. So there have been studies in Germany, there have been studies in the US, and they've all shown that if you had a perfectly, like a perfect sheet of gypsum board or what have you, that had no leaks whatsoever, and then you put some moisture on one end and you had the other side dry, and then you try to calculate how much moisture would pass through that assembly by diffusion alone, it would be quite a small amount. Whereas if you introduce a small gap, and then here in this study, they just introduced a 1 millimeter gap, they realized that through that 1 millimeter gap, there's 1,600 more times moisture that is carried by air leakage, so by pressure differential, than just through diffusion alone. So by stopping air leakage, we can solve a lot of our moisture problem. And Joe Sheberg, who's a famous building scientist, I mean, he notes that if you want to, you have to start with your water problem, then solve that, then solve your air tightness problem, and then you can address your diffusion problem. Don't try to address your diffusion problem if you haven't solved your air tightness problem, because diffusion is so much slower than air leakage. And then this is a study from Building Science Corporation from Joe Sheberg. And then he showed that, like, through diffusion alone, you have about 0.3 liters of water that are collected. But through air leakage, just a 1 square inch hole, you get about 30 liters of water collected. So air carries so much more moisture than water does. So why are we so obsessed with diffusion? Why are we insisting on vapor barriers? And like we seem to think that, like, sometimes at least, that the vapor barrier is kind of like the more important thing, or that they're equally important. Well, it all started with this gentleman here. His name is Frank Biroli, and he was a professor of mechanical engineering and also the head of ASHRAE back in the 1930s. And his theory was that basically he was a mechanical engineer, and it was the introduction of air conditioning in assemblies. And his theory, and they realized that by using more materials that were like less prone to diffusion, they could improve air conditioning systems. So he applied that to buildings without necessarily also thinking about other moisture transport mechanisms, such as air tightness. And if you read this quote, basically it says, and I will share the recording and the slide deck, but it basically says that you had, this was written by a gentleman way back in 1923, and he was suggesting that in order to insulate properly, you had to make it as airtight as possible, because if you let air in, you would also let so much more moisture. But that didn't really take on, if you will. And Raleigh was so influential that, when insulation was introduced, he applied his vapor diffusion theories around the 1930s. And, there was a lot of politics. There's a great article by William B. Rose that kind of like explains how, we came with so much vapor, so many vapor barriers in our buildings. But basically, if you look at the progress, in the 1940s, there was these regulations that now started introducing a requirement for a vapor barrier in the buildings, not talking about air leakage at all. And then that became kind of like the beginning of this, vapor barrier craze, if you will. And most of the assemblies performed okay for a really long time. But in the 1980s in Canada, we started realizing that we were getting a lot of like attic moisture and mold in residential houses. And that was due to a switch to electric heating, because with electric heating, you're not creating as much ventilation. So there was a lot more moisture that was getting brought in through air leakage. So we realized that, and then we kind of like created this term called the air vapor barrier, because we already had polyethylene, and we said, hey, if we tape all the joints and we seal all the penetrations, we can turn that vapor barrier into an air vapor barrier, because the vapor barrier is already so popular, people understand it. But if you look at polyethylene, you know how it's installed, you can see that it's not really a material that's made to be airtight. And, the building science industry cried foul, but unfortunately they were not listened to. But right now we're kind of like in this period here where we're starting to re-understand the benefits of airtightness. And that's where, some of my beef comes, where I say, okay, well, if you're saying air vapor barrier, what you're not realizing is that it's essentially a remnant of the past, right? So it wasn't something that was used to originally describe polyethylene. And it creates obfuscation because it conflates the distinct requirements for air control and vapor control in wall assemblies, because it kind of like merges both terms, right? Apple and oranges is not the same thing as apple/oranges, right? Tom/Jerry is not the same thing as Tom and Jerry. We want both. A lot of times we want both air control and vapor control in our assemblies, but air vapor barrier kind of like obfuscates that term, and then it gets thrown around to just describe any kind of membrane, really, basically. And then I find that there's this unintended emphasis on vapor diffusion because it's the vapor barrier that's yet at the end. The air part is kind of like air what? Is it an air or vapor barrier? Is it an air and vapor barrier? So that can lead some, people who are not as understanding, or even homeowners, to think that the vapor barrier part is the more important part. But we've seen that air control is way more important. And with manufacturers introducing these different new membranes that are vapor permeable, semi-impermeable, and what have you, this kind of like, I find that this term is no longer suitable, if you will. So what do I propose? The easiest way to solve my personal beef, if you will, would be to call it for what it is, right? So call it an air barrier / vapor retarder, right? If you still want to use the /, right? So just say that it's an air barrier and say that it's also a vapor retarder. Because when we say air vapor barrier, we're just really trying to note a material that does both functions. Another alternative would be to call it an air and vapor control layer. That's been used successfully in Europe for many years, and they understand that terminology and they have no problem with that, because that way you can really start playing around with the different permeance ratings, air leakage ratings, and what have you, if you just call it an air vapor control layer, and then in your specification you define what the air and vapor control layer is. And this is my suggestion, like, since we already have descriptions for vapor barriers, why don't we just kind of like tag to the air barrier description, what that material is, right? So it could be a vapor permeable air barrier, it could be a vapor impermeable air barrier, it could be a semi-impermeable air barrier, and so on and so forth. So by doing this, we're really clearly communicating to the contractor what the role of that membrane is and how permeable or non-permeable it should be. Okay, I think that's the end of my slides. So if there are any questions, I'm happy to take them now.
Thank you, Juiced. We'll go ahead and take some questions. It looks like we've got one here. James asks, since we have reverse vapor drive, what do you think would be the optimal permeability of an air barrier?
So that's a hard question to answer, just I guess not by knowing the specific climate and the specific situation that you're speaking about. But what has been recommended is that in cold climates such as Canada, most of Canada, you would just need a vapor, like a semi-permeable membrane. So something just like craft paper or even like latex paint could do the job. That said, the building codes don't necessarily allow that now. So in order to do that, you would have to show through some kind of like hydrothermal analysis that you're not building up too much moisture, and your code official would have to agree to it. So it's not like, I mean, I want to also try to stay away from rules of thumbs, if you will, because every climate is different. And, now that we're throwing climate change as another variable in the mix, it makes things even more difficult to predict. Did that answer your question, James? Okay. Are there any other questions? No. Okay. It doesn't look like it. So I think we can. Oh, are you proposing code changes? Not. I am not proposing code changes. But what I plan to do is I plan to propose standard changes. So I plan to speak to the ULC and propose that as they describe their air barrier systems, that they put emphasis on the vapor or the permeability description of the air barrier so that we have better terminologies. So yes, I plan to do that.
Any other questions?
I think somebody is typing. Oh, you're very welcome, Sokrat. Okay, so somebody has a question. Great presentation. How does this vapor barrier help in a hot climate like India? So I think that it's for most hot and humid climates. You have like, temperature, but you also have humidity. So you have to take both into account. And often in hot and humid climates, unless you have a very specialized type of building, like a refrigeration plant or something like that, you definitely do not need a vapor barrier. Air tightness is always important. So if you're going to provide some kind of air conditioning or what have you, that's important because you don't want to leak that air conditioning out of the building. But in a hot climate, usually vapor barriers are not required. And that's the problem, is that I think the vapor barrier was kind of like applied point blank across, the entire United States, and it created some really difficult situations in hotter climates like Florida, for example. So usually it's not as like in a hotter climate, those wouldn't be required. But again, like I think that there are many manufacturers out there that offer like hygrothermal modeling services. So if you're in doubt, always try to reach out to a consultant to get some of that information. Okay, maybe we'll take one last question if there are any. If not, we just want to be mindful of everybody's time. So maybe we can wrap up, Ashley.
Great. Thank you, everyone. We appreciate you all being here. As discussed, we'll send you a recording of the webinar as well as some additional documentation by email as a follow-up. Please remember to check your spam folders if you don't receive it. If you have not already done so, please sign up for a free Bibliotech account at www.bibliotech.ca, where you can connect with hundreds of manufacturers and suppliers to assist with your projects. We also send out a free monthly newsletter where we share exciting events like this one. If you'd like to follow us on social media, our handles should be on the screen. And finally, there is a post-webinar survey that will appear when we end this session. If you could take some time to fill it out, we would really appreciate it. Thanks again for joining us today, and we hope to see you next month.
Thank you very much, all. Take good care.